Hi guys, today we're going to look at integrating exponentials, but where our base is not e. So up to this point we've dealt only with the base e, and so now we're going to look at how to do other bases. Okay, this is a pretty quick and simple topic, and we'll practice tomorrow and then we will move along. Okay, so what we need to know here is that there's actually two ways to approach this. And the first way is we can convert to e, so we can make it look like what we've been doing, okay? And we do that by taking a to the x, so a would be our other base, okay? And we could just rewrite it as e to the natural log of a, okay, times x, which is okay, but we do not have to do that. Okay, the other way we can do it is by using this theorem that says the integral of any base a to the x dx is equal to 1 over the natural log of a times a to the x plus c. So since we have this formula, this is a way I personally would prefer to do this, and so that's how I'm going to show you how to do it today. Okay, so since we have this equation or this formula, let's do it this way. Again, the important part is that this base is a. Okay, and notice it just shows up here and here. Okay, so we will just be looking for simple exponential functions that don't have e as a base. Okay, so let's take example 1, and we have the integral of 2 to the x dx. Okay, and again, remember when we're finding integrals, we are looking for the area under the curve. If we had this from a lower limit to a higher limit, then we would be looking at the area from like left to right. But here we're just talking about the entire curve. So what is our a in this case? Okay, well, a is just 2. And so using this equation or this formula from up above, we can just rewrite this as 1 over the natural log of 2 times 2 to the x plus c, and we are through. Okay. If you'd prefer, of course, you can put 2 to the x over natural log of 2. Okay. If you don't like natural log of 2, you could always use a decimal approximation as well if you wanted it in front. So you would take 1 divided by natural log of 2. But anyways, so that would be your most basic example, right? We just have a very simple exponential function. Okay, so what about if we have a similar one, but we have a definite integral this time? So this time we do have a left and right limit. We want to integrate our function from -1 to 2. We want to do 3 to the x dx this time. Okay, so this does fit our pattern. Our a this time is just 3. And so we would have 1 over the natural log of 3 times 3 to the x. Okay. And then we would need to put in our -1 and 2. Okay. Since we do have the definite, right, the limits. So now we just plug in. So I'm just going to rewrite this as 3 squared over the natural log of 3. And remember, we subtract when we do our endpoints in there. Minus 3 to the -1st over natural log of 3. Okay. And there's different ways you could write that. But if we wanted to go ahead and find that in our calculator, then we would have 3 squared divided by the natural log of 3 minus 3 to the -1st divided by the natural log of 3. And we end up with approximately 7.89. So when we have a set of limits, the -1 to 2, decimal approximations are perfectly fine as well. If you wanted to, this would also be, if you went through the fractions, this would be 26/3 times 1 over the natural log of 3. Okay, so just kind of depends how you want to work it out. At this point, I would just use my calculator, okay? And that natural log button is right next to the 4, typically. Okay, so there's an example of a very basic one by itself and a basic one where you have to plug in your specific endpoints. Okay, so let's look at one that's a little more involved looking. So here we have 3 minus x times 7 to the 3 minus x quantity squared times dx. Okay, and so this, I would agree, would look pretty complicated, but if we think about how does it fit what we're doing, we're looking for a base, right, taken to a power. And so this 7 is very suspicious that this would be my a. Okay, and then we are going to have to do something with this u up here, okay, right, or this function. So let's go ahead and let it be u, because we know how to deal with u's, even if they didn't come out and tell us what to do. Okay, so u is equal to 3 minus x quantity squared. Okay, and you could just do 3 minus x, but it's probably going to be in your best interest to go ahead and do that whole thing. Now, it's been a while since we've had to do this because this is the chain rule. We could let v equal 3 minus x and use the power rule, or we can just do the chain rule here where we bring the power down. So it's going to be 2, and then we have 3 minus x because you take it times that inside function, and then we take the derivative of that inside function, which is -1. Okay, so that's our chain rule, right? That power, we bring the power down, and then we take this and take the power -1. Okay, and then we take the derivative of the inside. So now we have 2 times 3 minus x times -1 dx. And if we look over here, we need just a 3 minus x and a dx to be able to rewrite this in terms of u. Okay, so I need a 3 minus x and a dx left. So that means I need to divide by this -2. So I get -1/2 du, or du over -2 is equal to 3 minus x dx. Okay, so that's what we have been doing recently. Okay, so now let's go plug in here. So 3 minus x dx is taking care of that -1/2 du. Okay, and then I can just leave this as 7, but this is 7 to the u. Okay, so then let's go ahead and use our power, or excuse me, that new formula that says if I have this exponential, then I can rewrite this as 1 over the natural log of our base, which was 7, okay, times a, which was 7, to the x, which in this case we need it to be u. Okay, and then we would have plus c. Okay, and then we'd go back in and plug our u back in. Okay, so we'll get a -1/2 times 1 over natural log of 7 times 7 to the 3 minus x quantity squared. Okay, and then we can't forget our c. Now there is, and this is perfectly fine, there are a couple different ways you might see this written. Some people would go ahead and change that to x minus 3, which it's not going to matter because if you square that, you'll get the same thing. What else? Oh, this -1/2. Do you remember about your logarithmic properties, what you can do when you have a number in front? Okay, well, this is actually a power. And so this could also be written with a negative. Okay. And then this 2, like this, you can leave the 1 on top, but you could take the second. This is a second power. So this could also be written as 7 squared because of that 2 right here. So this is actually the same thing as natural log of 49, okay, times 7 to the 3 minus x quantity squared. Okay, so that'd be an alternate way someone might write it. Okay, because with logarithmic powers, a number in front is a power, and so you could bring that up. Okay. So there is that one. And one more. We can't forget about our trig functions. Okay. So although we might want to. So let's try the integral of 2 to the sine x. Okay, so that's where that power comes in, right? We have the 2, and then we have an exponential up here. We have an x in the exponent times the cosine x of dx. Okay. So again, we do have a base other than e, but that can be our a. And then this is our exponential part. So if we'll let u equal sine x, then when we take du, we get cosine of x dx, okay, which is good for us here. Because we are now able to cover that cosine x dx with our du. So we can rewrite this as 2 to the u du, okay, which then lets us use our rule that we can take 1 times the natural log of our a, which is 2, times our 2 to the u. And then we just have to go back in and plug in for u. So we have 1 over the natural log of 2 times 2 to the sine of x plus c. Okay, so even if we have something more complicated up in that exponent part, you can just let it equal u, and then hopefully it'll give you that du to work with. Okay, so that's all I wanted us to talk about today. Tomorrow you'll have, I think, 3 problems to deal with on that, and we will move along. So hope you have a great day.